In this video, I'm going to explore the common ion effect and show you how we can calculate the effect of adding a common ion to the solubility of a sparingly soluble salt. A sparingly soluble salt such as silver chloride. If I dissolve not very much silver chloride in some water, I set up this equilibrium where I have a saturated solution. The ions are in contact with the silver chloride solute. What happens if I then add a common ion to my saturated solution? Let's say I add some sodium chloride. Well, the Chatelier's principle tells us that if we increase the concentration of the chloride ions, the position of equilibrium will shift to the left. That in a sense means that we're going to be taking silver ions out of solution. Silver chloride will start to precipitate. We are decreasing the solubility. So addition of a common ion decreases the solubility of our sparingly soluble salt. Let's put some numbers to this. Calculate the solubility of silver chloride in pure water and in 0.15 mole per decimeter cubed sodium chloride solution. Okay, so the first bit is pretty straightforward. We need an expression for solubility product. KSP is the concentration of silver ions multiplied by the concentration of the chloride ions at equilibrium. And since it's a 1-to-1 ratio, we can call each of those x. So 2.0 times 10 to the minus 10 is equal to x squared. So the solubility is 1.4 times 10 to the minus 5 mole per decimeter cubed. Now, we're expecting the solubility to decrease when we are trying to dissolve silver chloride in sodium chloride solution, the common ion effect. So let's see to what extent that happens. So B, I'm going to start with the equation again. So we've got some silver ions and some chloride ions. Now, initially, my initial concentration of ions, that's in mole per decimeter cubed. Before I add any silver chloride to my sodium chloride solution, I will have no silver ions. But the concentration of the chloride ions is 0.15 mole per decimeter cubed. Once I've added silver chloride and my solution is saturated and I've allowed it to reach equilibrium, my equilibrium concentration, well, we don't know. I'm going to have X number of moles of silver ions, and I'm going to have X plus 0.15 mole per decimeter cubed of chloride ions. So the X is the amount of chloride ions from dissolving our silver chloride, and the 0.15 comes from the sodium chloride solution that's providing the common ion. So when I put that into my expression for KSP, KSP is 2.0 times 10 to the minus 10 is equal to X times X plus 0.15. Now, we're going to make an assumption to make this calculation easier. We know that in pure water, the value of X is really very small. It is, well, we worked it out, 1.4 times 10 to the minus 5. That is considerably smaller than 0.15. It's so much smaller that we can assume that it's negligible. And in fact, since we know the position of equilibrium is going to be shifted to the left in the presence of our common ion, this value of X is actually going to be a lot smaller than 1.4 times 10 to the minus 5. So we're going to make an assumption. We're going to assume that x plus 0.15 is essentially the same as 0.15. Now, 2.0 times 10 to the minus 10 is equal to x plus 0.15. So x, the solubility of silver chloride in my solution of sodium chloride, comes out to be 1.33 times 10 to the minus 9 mole per decimeter cubed. Now I just want to take a minute to have a look at this. Times 10 to the minus 9. Dissolving silver chloride in the presence of a common ion has reduced its solubility, well, from 10 to the minus 5 to 10 to the minus 9 by 10,000 times. Silver chloride is 10,000 times less soluble in my solution of sodium chloride than it is in pure water. That is the power of the common ion effect. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.